Welcome AP. This is a new day and a new chapter. We got chapter 4, kinetics. In the College Board curriculum, kinetics is its own unit. So all of Unit 5, everything that we do in Unit 5 is all this one chapter. So that means this chapter is huge. So you're talking about at least 10 to 15% of the AP exam is kinetics, okay? So we want to rock kinetics, and we usually do because there's a lot of math, okay? So number 1, 14.1, what affects reaction rates? So Unit 5.1, this is the learning objective. Take a minute to read all three. We're going to look at how reaction rates get affected 4 different ways. But take a minute, annotate, make some notes so you know what AP expects you to know. Kinetics is the study of speed, or how fast a reaction occurs, by changing various conditions. The conditions that we're going to be changing is we're going to be changing some concentration, definitely temperature, pressure, maybe some volume, heck, even moles. Okay, doing dilutions. How fast can a reaction occur? Okay, so reaction rates, they depend on collisions. You need collisions in order to have a reaction. So the more collisions you have, the faster the reaction. So we have something called collision theory of reaction rates. And in order for a reaction to actually take place, all of the following must occur so you could actually have a reaction. Even if just one of them, one of the 5, then you're not going to have a reaction, okay? So what are the 5 collision theories for a reaction to actually occur? Well, 1, you got to have collisions. So with these collisions, you got to have the molecules collide with each other, okay? So you got to have collisions. Only 2 particles can collide at a time. So basically there is, and I believe it's in 14.5, we're going to talk about how it is truly impossible to get all 3 collisions to happen at one time. Okay, on paper I can do it very easily. Okay, but in order for you to have a collision, you have to have all 3 collide. And that's just impossible, okay? So, does not occur in real life. But I can get 2 molecules or atoms to collide. They got to have proper orientation. Same thing, 14.5. We're going to talk about how they have to be lined up in order for them to collide so that when they come in contact with each other, they actually become products. So maybe you have like a diatomic and then this diatomic trying to come together, and that's not going to happen, okay? You want to have them lined up in the same orientation to come into contact with each other. Or maybe they're diatomic this way, and they come and contact with each other. Okay, so same thing, 14.5, we're going to talk about that orientation. They got to be lined up in a certain way. The collisions must occur with enough energy so that the electrons can rearrange and form new bonds. This also is in 14.5, where we're going to talk about something called capital E little a, activation energy. You have to have a certain amount of energy so that way you can break whatever bonds and form new bonds. So in this energy, you're breaking bonds so that way the electrons can rearrange, okay, and then forming new bonds. And then if you actually have all 4, number 5, the new collision product is at the peak of the activation energy hump, and it's called the activated complex, the transition state. At that transition state, you have broke any bonds that were needed. Not every bond, just whatever bonds that you needed. So there is a graph coming our way. Big time graph. Looks like this. Okay. Now whether it ends up here or ends down here, we'll get to that. But this right here, let me label it, this starting energy, and up to this hump, as you see right there, this is that EA. This is that energy needed to get the reaction going. But then when you get to the very top of the hump, that's called the activated complex. Okay? We're going to go into great detail, same thing, 14.5. We're going to go into great detail with these graphs. But even if just one of these 5 conditions aren't met, you don't have a reaction. So it's really really amazing how we actually get a reaction to occur. So let's look at 4 things that can affect the rate of a reaction. So anytime you increase collisions, you make it go faster. Okay? So the molecules are speeding up. Okay? You not only have it go faster, but you can also produce the products that you need even quicker. So first we call the nature of the reactants. There's 2 criteria of what we mean by nature of the reactants. So first, is it a solid, liquid, or gas? I mean, obviously gases have more kinetic energy, so they will be faster. Solids, very low kinetic energy. Okay? You're not going to get collisions with solids, no collisions, because remember, the particles aren't moving from one location to another. Okay? Remember, they're just sitting there vibrating. Okay? So you're not going to get any collisions there. But there is a way for us to take a solid and to do something with it to get a reaction faster. What if you had a solid and only the particles of the surface of the solid are available to react? So what happens is, say you have like a cube, like a sugar cube. What happens is the particles that are only on the surface, that is the only ones that you're able to come into contact with, not the ones on the inside. On the inside are being protected, okay? And we call that surface area. If the solid is broken up into little pieces, the surface area actually gets larger, which means now you have, here's the key part, you have more particles available for collisions. And if you have more particles for collisions, the reaction is faster. So the rate for smaller particles are greater because the surface area in contact with each other of the other reactant is greater. So for example, if you take like a large piece of wood, it burns very slowly, okay? So when you have like a piece of wood, because it is huge, all you're able to do is attack the surface. But if you actually then take that piece of wood and break it up, it'll go faster. And then, if you've ever been in like a cabinet shop, sawdust is actually really explosive. People that make cabinetry have to be very careful every time they cut wood or sand wood. All that dust, if there's a spark anywhere in that building, it's going kaboom, okay? So every time you get to like smaller and smaller and smaller, and then you got fine little particles of dust, okay? That is the fastest reaction. Also, who is the actual chemical? Who's reacting? Ions are the best, okay? They're actually very fast. But if you have somebody with like, let's say it has like 2 bonds versus somebody that's got like maybe 4 bonds, or maybe somebody has 6 bonds attached to it. Kind of looks like a little star pattern. The slower it is. So the less bonds you have are actually faster versus slower, okay? So let's look at some examples. So say I have calcium carbonate solid, and it looks like I add maybe some acid, some H+, and then I get the following products. If I have powder versus pellets, So notice what's different. So I always like to keep track of what's different. So this is different. The volume of the acid is the same. The concentration's the same. And the temperature's the same. So what's the factor that's going to determine the rate? Well, powder versus pellets. So remember, pellets, okay, think of it like tiny little M&Ms, where those dipping dots, ice cream, those little tiny little pellets, versus powder, like sugar, like salt, okay? The initial rate of formation of that CO2 is represented in the equation above by doing two different experiments. Which experiment would be the fastest initial rate to form CO2? Well, the powder would be. I'm going to type because I know you guys love reading my crazy writing. So how do you explain to AP what's happening? Okay, so first you tell them the answer. So powder, CaCO3, will be a faster initial rate of formation, okay, of CO2. You always want to throw the question back at them. Then pellets, okay, that is a criteria. You have to tell them which one you're picking versus comparing it to the other one. You always have to mention the other one, even if it's not the winner, okay? Due to, now what's the criteria? It's the surface area. Due to larger, or you could say greater, surface area and more particles are available to collide with each other. Okay? Get to the point. Who wins, then the other one, and why does it win? Okay? All right, so hopefully that right there made it easier for you to read my crazy writing. Okay? Concentration. Okay? When you have something that's like 1 molarity versus 6 molarity, well, remember back in chapter 4, molarity is moles over liters. Okay? So if I have 1 molarity, that means I have 1 mole per liter, or 6 moles per liter. Let me write the other one like the other way. Oops. There we go. So that means for the same volume, I have 1 mole versus 6. I have 6 times more chemical available to react. That's going to get you what? More collisions. Okay? So increasing the reactants by putting more reactants into the same space as in aka volume, okay, I still had 1 liter, increases collisions leading to a faster reaction. The reactants are not as far away from each other as compared to a lower concentration, because you got to remember in your sample, maybe you have like 1 mole in that one sample, versus now you have 6 moles. You've actually brought them closer together. This molecule, well, it can only collide with the wall so many times, but this one can collide with each other, the walls, the next one, so forth, so forth. So in order to increase concentration, what must you do? Well, I think common sense means add more reactant, add more chemical, or add less water. Okay? Not a dilution. Dilution would make the concentration go lower. So add less water. Or if you're thinking about like gas laws, Mr. Boyle's law, if pressure goes up, volume goes down. If temperature and moles is constant. Okay? So what if you decrease the volume of a gas? So you went from a container that looked like this to a container that looked like that. So when we say decreasing the volume, we're not talking about the gas, we're talking about the container that it's in. So I had molecules that far apart versus now I have molecules that close together. And this would lead to less collisions. And because you brought them closer together, you would have more collisions, which means faster reaction. So increasing the pressure of a gas can be achieved by reducing volume, which leads to more collisions. Okay? So don't forget about gas laws, because gas laws are still fair game. Okay? Use that knowledge from chapter 10. So if I actually brought them closer together, I have produced more collisions, which means I have increased pressure because I decreased the volume. So look at the two scenarios. So now we have both powder, so that's the same. Volume of the acid is the same. But now, that's the determining factor. Less concentration, more concentration. But the temperature was still the same. So now, who will have a faster initial rate? Well, probably experiment 2 if you're thinking of what I'm thinking. So experiment 2 will have a faster initial rate of formation of CO2 than experiment 1. You can totally abbreviate the word experiment due to the higher concentration of H+. Okay, say who the actual chemical is, since it has more moles to react with. More moles of H+ leads to more collisions and faster reaction. There you go. Sometimes you need more than one sentence to say it, but you should be able to say any type of explanation in chemistry within 3 to 4 sentences the most. We're not writing novels in AP. So hopefully me typing is a lot easier than reading my crazy writing. So now, what's the big one? Temperature. Okay? Temperature, heat them up, speed them up. The faster they move, the more likely they will collide. I mean, temperature is always the one that we try to heat up the most. Okay? It is usually our first criteria of what we want to do to make something faster. So if you increase temperature, what are you gaining? Well, you're gaining energy. That's the key. That's why it's called kinetic energy, the energy of motion. So the energy of motion. Cranking up that temperature gives you a gain of energy, and now you have more successful collisions that are needed for that activation energy. Now, like I said, 14.5. Activation energy is that energy needed to get the reaction started. Okay? You always need energy in the beginning. Therefore, an increase in reaction rate with increasing temperature. I think it's a little common sense to me. So now if I have the same powder, the same volume, the same concentration, but now I have twice the temperature. Okay, that's the difference. So which one will give you a faster reaction? Well, I think we know experiment 2. So experiment 2 will be a faster initial rate of formation of CO2 than experiment 1 due to a higher temperature. You can abbreviate, okay? There are certain words you can abbreviate and obviously certain words you can't. I will show you every abbreviation you can do to save time. A higher temperature, let me capitalize. You want to do a little proper English. A higher temperature will lead to an increase in collisions and more kinetic energy. Higher temperature will lead to an increase in collisions and more kinetic energy that will increase the reaction rate. Ta-da! See how easy that is? Okay. Man, I like typing. I wish you guys could type too. All right. So that's 3 components. What about number 4? We in honors and CP, we did experiments when we got to the actual chapter of reactions. We added a catalyst. So that way you could actually see what a catalyst does, and it's an added chemical that speeds up the reaction. Well, if that's its one job, I mean, obviously it's going to increase the reactants. The catalyst is a substance that increases the reaction rate while remaining chemically unchanged. What do we mean by that? That means the catalyst has no part in the balanced equation. Okay? As in, there are no bonds broken with that catalyst. I'm breaking reactants and products, but what it's saying here is that the catalyst is a substance just to make it faster, but the chemical is not changed. The catalyst is still the catalyst beginning and end. But you're going to notice when we get to, I want to say it's 14.6, he's nowhere in the balanced equation, the overall balanced equation. Now, back in CP and honors, when we had a catalyst, this is the most famous equation that we did. We did it with hydrogen peroxide. That hydrogen peroxide was a liquid. We added a catalyst called MnO2, manganese dioxide. And what it did was it broke up into water and O2 gas. So in your test tube, you actually saw, with that hydrogen peroxide, you saw a whole lot of bubbles. And then you guys did this thing called a split test. And you took that split to test if there was actually oxygen. So remember with the split test, it was a glowing split test. And then you had like a little bit of red. Let me get a little color coding here. You had a little bit of ambers right there. So when you actually put it near the bubbles, you saw fire. Probably should draw actual flame. You had it ignite, because what does a fire need to burn? It actually needs oxygen. So that's what you guys did. You did a glowing splint test. You saw those bubbles from the oxygen, and that oxygen lit up the little ambers that are at the end of that splint test. So notice that MnO2, it's not a reactant, it's not a product. It's just an added chemical. But it has nothing to do with the balanced equation. Okay, so it's not changed. The catalyst usually works by providing an alternate route. This alternate route is what leads to a lower activation energy. So same thing, 14.5, you'll see what that alternate route is. It basically, this alternate route, lower EA, makes the reaction faster. Okay, it's like you got there faster by going a shortcut. Okay, so therefore more collisions are successful, and now the reaction rate is increased. Okay, so at 14.6 and 7, the catalyst is nowhere part of the chemical reaction, and it's not being used in this reaction. Okay, it's just an added chemical that's there to make it faster, and that's it. Okay, so hopefully before we go on to that next one, make sure you understand how the 4 conditions that we talked about can make a reaction faster or slower. See you on the next one.